So which of the following alkenes below could not exist as cis-trans isomerism? So just as a quick reminder, cis-trans is referring to the position of the hydrogens in relation to a fixed rotational barrier. So here's in an alkene is our fixed rotational barrier that's created by the overlap of two p orbitals, unhybridized p orbitals. And so cis-trans is referring to the location of the hydrogens. And if they're on opposite sides of the plane, let's say these are metals, if they're on opposite sides of the plane, then we're looking at trans. So this is a trans. If they were on the same side of the plane, then we would be looking at a cis configuration. And so that plays a role into the energy of the compound as well as some of its chemical properties and physical properties. You guys are learning right now about an EZ system, and your book explains how the EZ system is used because sometimes cis and trans, when you have more complex priority groups, will result in ambiguous names. And so ambiguous meaning kind of confusing or hard to understand, kind of hard to really get across the first time. And I'll give you an example of that. Let's say that instead of methyl groups and hydrogens, we actually had a more complex structure like bromine, chlorine, iodine, and methyl. So in this case, this structure would be trans. And it's ambiguous in the sense as what is trans? Are these two trans or are these two trans? And so that's why we use the EZ system in order to get a clear understanding of what are our priority groups. Bromine, chlorine, iodine, you guys know, you guys can relate those to one another, but sometimes you'll get more complex branches, like let's say just a ton of alkanes for all four of them. And so the EZ system gives you the ability to kind of lose that ambiguity when you're seeing the configuration. And so E is the same thing as trans, and Z is the same thing as cis. So you wouldn't be wrong in calling a cis compound that it's in a Z configuration or saying that an E compound is in a trans configuration because it's the same thing. The second system, the latter system, was just developed to remove the ambiguity. So in this case, we would split, practicing the EZ, we would split the planes, and the left plane we would prioritize. So iodine has a greater molecular weight than a methyl group or carbon that it's attached to, and so iodine takes the priority. And then on our right side, the bromine has a greater molecular weight than the chlorine, so the bromine takes priority. And so now we want to see how our priorities relate to one another. In this case, they are on the opposite ends of the fixed rotational barrier, and so this would be E or trans. Okay, so that's just a little bit of concept, but let's go ahead and just knock out this question real quick. What stops us from having cis-trans isomerism? And so what the definition of a cis-trans, which you have to have, is opposite molecules, or I'm sorry, different molecules on both ends of the fixed rotational barrier. And so you can't have two hydrogens, you can't have two methyls, two ethyls, you have to have different compounds in order to have a cis-trans isomerism. So you have to have, even if it's the same compounds, but they have to be opposite on either side of the fixed rotational barrier. So that's what we're going to look for in this case. And once you get really good at drawing these out, you can actually draw them mentally. And so you could imagine 2-pentene in your head rather than drawing it out. But we're going to draw it out in our case. We still need some practice. Here we go. So we've got the 2-pentene, and I've already drawn the trans configuration for you. And what makes it trans is the fact that on the hydrogens on the opposite sides of the rotational barrier, that being the double bond, are on the opposite sides of the plane of the fixed rotational barrier. And so that makes it trans. If we wanted to draw the cis product of this, that's where I would just draw my double bond first, and then I'd add my methyl group, which is priority over hydrogen. And then we're looking for cis, so we want to put our priority groups on the opposite ends on the same face of the fixed rotational barrier. So in this case, this ethyl group, rather than putting it on the opposite end, we're going to put it on the same. Okay, and then our hydrogens are going to be over here. And so this compound is now, not this one, this compound is our cis configuration of 2-pentene, because the priority groups, our first priority groups, are on the same side of the fixed rotational barrier. We could also call this a Z configuration. Okay, so now let's continue going through the remainder of them just real quickly. B, 2-methyl-2-pentene. And if you try to put this as a cis trans, you're going to run into the problem that it does not fit the definition of cis trans, because it has 2 methyls, which are the same molecule, on one side of the fixed rotational barrier. And so that breaks our cis trans, because no matter how you orientate this, it's going to be the same compound. So let me go ahead and kind of show that to you. You can't prioritize them also, because methyl and methyl are the same thing, so you can't give either one of them a priority. But if we were to try to switch this over to this end, like we do when we're doing a cis trans, we just switch one of the molecules on either end, we just switch it over to the opposite end of the plane, and that gives us our opposite configuration. If we were to try to do that with 2-methyl-2-pentene, we'd run into the problem that you're going to get the same compound. So now, instead of it going over here like it does in this configuration, I drew it on the downward end over here. But that's still the same compound, because if you were to flip it, it's our normal line angle structure with a 2-methyl coming off. So this is just essentially the mirror. This is the mirror of this guy, but it's still the same thing. There's no cis or trans. You saw in our 2-pentene, how the cis and trans look very different. In this case, they do not. And so we'll do just the remaining two, just to emphasize that, the difference between the cis and trans configuration. Here we've got trans 3-methyl-2-pentene. Trans because the priorities are on opposite sides of the plane. So here's our methyl priority, takes priority over the hydrogen. And then our ethyl takes priority over the methyl. And so since they're on opposite sides of the fixed rotational barrier, they are trans. And then if we were to draw the cis, we draw our double bond. We're going to keep the methyl in the same place, but in this case we're going to switch these groups. And so we're going to draw the ethyl down here and the methyl over here. And this has a much different structure and different energy characteristics than the trans. So that's cis, and the other is the trans. Okay, and so last one. What makes this trans? What makes it trans is that the priority groups, or the hydrogens, are on the opposite sides of the fixed rotational barrier. So we've got our priority group and our priority group, in this case being an isopropyl, and they're on opposite sides of the rotational barrier. So that makes it trans. If we wanted to do cis, we draw our double bond. And then we're going to keep our methyl the same and our hydrogen the same. And then we're going to switch the isopropyl group to this bottom location. We're going to put it on the same side of the plane. And then this is going to be our hydrogen over here. I'm sorry, our methyl. And this would be the cis configuration. So hopefully that all made sense. Just keep in mind when you're looking for what stops it from being cis-trans, in this case B, is the fact that you have to have different molecules on both sides of the rotational barrier. You can't have 2 methyls or 2 hydrogens, and so that's what stops 2-methyl-2-pentene from being able to have a cis-trans isomerism. You can't switch the locations of it and get a different compound. And in the other case, for the remaining 3, you can do that.